All right, everybody, welcome back. Let's talk about Chapter 17 from the 209 book, Calculus Treatment, the Calculus Treatment book, Dr. Katz's book. And let's look at problems from Chapter 17. From Chapter 17, let's look at problems 16, 22, 24, 49, 50, and 70. Let's start. I didn't quite write everything down there for number 16, but I'm going to do it right now. For problem number 16, they give us a wave function looking like this. All right, there's what the wave function looks like, guys. We are going to take this wave function and we're going to do a whole bunch of things with it. If we change the wave function a little bit, we're going to see that there's a lot of predictability as to what happens when we change any wave function, how it compares to what things were like earlier. So that's kind of the deal. This is what we're dealing with, and we're going to manipulate this to do a lot of the problems that we got to do. So for problem number 16, let's take a quick, let me just read it really quickly to you guys, and we'll see what we can do about it. For problem number 16, a harmonic transverse wave function is given by what I just wrote on the board, ladies and gentlemen, where all values are in the appropriate SI units. A, B, C, D. A, what are the propagation speed and direction of the wave's travel? B, what are the wave's period and wavelength? C, what is the amplitude? D, if the amplitude is doubled, what happens to the speed of the wave? Okay. Again, all of this is on Canvas as well, guys. Later on, I'm going to try to do some problems that are in a different book, but even that different books, the problems are listed in Canvas for you from the Kutnell and Johnson book. But this is not it. Kutnell and Johnson, 10th edition. But I have some problems listed there for you that I was given permission to do so when I talked to the book rep. So that's down the road. There's two problems from there that I think you might find of interest. We'll get to that when we have to get to it. First things first. There's your wave function. What's going on here? For A, because of the plus sign, the wave travels in the negative direction. That's to the left. What is the speed? Well, okay. There's a lot that can be done here, guys. You got to remember, let's kind of, maybe this helps. We already have all the background that we need. We have the background that we need, you guys. That's the amplitude. This is the sine function. This is kx plus omega t right here, and that's the whole deal. Now hold on. Isn't k equal to 2 pi over lambda? Yes. Isn't omega equal to 2 pi over the period, which is the same as 2 pi, which is the same as 2 pi f. So 2 pi f for that right there. So either one works on there. I got to talk to you. If you were to take omega, which is 2 pi f, and divide it by 2 pi over lambda, you'll get lambda times f, which is equal to the speed of the wave. Well, wait a minute. That right there is omega. This right here is k. And what you got, especially right here, v is equal to omega over k. True. So what's going on here? What are they asking? Well, for A, because of the plus sign that's right here, we've talked about this in the past. Because of the plus sign that's right there, you guys, the wave travels in the negative direction. In negative direction. Travels to the left. The speed, 2 pi f over k, The speed is omega over k because it's 2 pi f divided by 2 pi over lambda. Well, what's omega? Omega is this, and k is this. So it's all the appropriate units are in place. 0.680 meters per second is the propagation speed. Not the speed oscillating up and down, the speed at which it travels sending those oscillations up and down. The speed of the wave is the wavelength that is accomplished, an entire cycle. Where will that entire cycle take place, and how long does it take for it to happen? So there's an entire cycle that will happen somewhere else. The first time that happens, that distance from the initiation point to where it first happens, that's the wavelength, and you divide by the period t, how long does it take for one full oscillation to take place a distance lambda away? Well, it's lambda divided by t. You know, v is going to be lambda divided by the period. 1 over t is the same as f, and that's where you're getting this. And all of that, though it doesn't look like it at first glance, omega over k will get you there because of what we talked about just here. Okay, so that's A. B, they're asking what is the wave's period and wavelength? What are the wave's period and wavelength? So, we know a lot of things. We know that omega is 2 pi f, or 2 pi over capital T. What do you say you multiply by t on each side and divide by omega? There's a number of ways you can do this. What did we say omega was again? Omega was 10.4. .604 seconds. Yeah, absolutely. What about the wavelength? Well, we could play that with the wavelength too. K is 2 pi over lambda. It's the same kind of mathematical games. Multiply by lambda on each side. Multiply by lambda on each side and divide by k. Two pi is 2 pi. K, well, they told us what k was too, you guys. It's 15.3. Here it goes. 0.411 meters. Yeah, absolutely right. They're asking you for C, what is the amplitude? What is the amplitude? Guys, mix and match all this stuff. That is amplitude. Amplitude is equal to y max is equal to A. I put A there. They sometimes don't put A there. Doesn't matter. It's all a linguistic issue that's not really an issue. Y max equals A is equal to 0.850 meters. Correct. D, they're asking a question. D, they're saying if the amplitude is doubled, what happens to the speed of the wave? Nothing. Doubled? Heck, I'll make it 1,000 times bigger if you want. If I made this thing 1,000 times bigger, the amplitude would go from 0.850 meters to 850 meters. Assuming I could do it. There's a lot more energy in that wave, that's for sure. But the propagation speed wouldn't change. It's, multiply it by 10, multiply it by 100, multiply it by 1,000, 1,000,000 if you want, if it's possible. Let's say it were possible, hypothetically. If you multiply by 1,000, so to speak, you get 850 meters would be the amplitude. That doesn't change omega or k. If you don't change omega or k, you're not going to change the speed of the wave. The speed of the wave remains unchanged. A change in amplitude by itself does not affect wave speed. So that would be D. No effect. And that's 16. Let's go to 22. A string of length, capital L, and mass, capital M, hangs freely from a fixed point on the ceiling. A, determine the propagation speed of the transverse wave traveling along the string at any position Y. Hint, the tension is not constant throughout the string. The tension at any point along the string is equal to the weight G dm of the string below that point. Determine the time required for a transverse pulse to travel the entire length of the string. Okay, this is rather interesting. Dr. Katz's discussion, ladies and gentlemen, Dr. Katz's discussion in this problem, as in many other problems, is quite brilliant. Let's see how this all played out. Now, this is definitely a calculus problem. For those of you looking at this without the calculus background that are not in my calc-based physics class, it might be a little different story for you. So just kind of watch out for that. See what we can say about this here. This is there's a number of ways we can say something here. Let me let's kind of look at that if you don't mind. Try to make this very clear. You are compelled to use calculus on this one. It shouldn't be too bad. Again, primarily this is directed to the 209 class. So we're going to look at it calculus based on this one. Many of the problems can go. We can mix and match them. There's a lot of non-calc based problems that you're going to find in the calculus based class, and they're excellent problems. So they're good for us, good to look at. Here, calc-based problem in a calc-based class. So let's be careful. Let's get it under control and see what's going on. Well, let me try to see what I can say. Well, there's a string of length capital L, and there's a string of length capital L and mass capital M hanging freely from a fixed point on the ceiling. So it's hanging freely from a fixed point on the ceiling. It's got a mass of capital M and a length of capital L, and it's a uniform string, you guys. Determine the propagation speed of a transverse wave traveling along the string at any position Y. The tension is not going to be constant throughout the string. This is important. The tension at any point along the string is equal to the weight G dm of the string below that point. Determine the time required for a transverse pulse to travel the entire distance. This is a great problem. The way you're going to look at it, the traveling in the x direction, or in this case the y direction, that's not a big deal. The travel speed of the wave is force tension divided by mu. Mu is the mass density, is the length density of the rope. In other words, what is the mass of the rope per unit length? If there is a tremendous amount of tension, on the rope, and you pluck it, and you make the pulse move, there's a tremendous amount of tension on the rope, and it's not a lot of mass associated with the rope, but there's a lot of tension, it's going to go really fast. If the tension force is very big and the linear mass density is very small, big divided by very small is huge. The speed is going to be a big answer. If there ain't a lot of tension, but it's a very massive amount of rope per unit length, it ain't going to go that far. Small divided by big is going to be small answer. Anyway, this is kind of the bread and butter of where we are. This is kind of on our mind for much of the problem. Now let's make sense out of the whole thing. The mass density, ladies and gentlemen, is going to be, that's mu. The linear mass density is going to be the Greek letter mu divided by L. I'm saying m divided by L. Capital M divided by capital L is mu, the linear mass density. In this case, the rope's up and down, guys. So I wrote it like this initially, true, and then later on in my notes I write it v sub y. Might as well make it honor the whole system that we have here. That's not the big deal. The big deal is, look at this relationship. It's kind of going to run the show to a big degree. If you had this, and we got, I'll tell you what I'm going to do. I'm going to call the bottom of this thing right here. It's attached up there. I'm going to say up here, this is y equals L. Down here, this is y equals 0. The length of this thing is capital L, right? Going up, y increases. That's the language we're going to use on this thing. Well, how do you want to do this? Well, this tension force, you guys, is equal to the amount of mass that's underneath a point under consideration. I'm going to make a long story short on this one. Right here, y equals 0 means there's zero length. Y equals 0 means there's zero length of rope underneath here. Y being equal to something else, y being equal to y up here, this y right here means you climbed up the rope y units. That means there's y amount of rope below you. How much amount of mass is, it's only the mass below you that counts. The mass below you is the linear mass density times the length of rope underneath you, which is y. So basically it comes out to the tension that's going to be in the rope at any particular point is going to be, you can play it a whole bunch of ways. The linear mass density times y, that'll give you the mass of y amount of rope times g. What's that equal to? Well, that's this right here. That is capital M over capital L times y times g. True. And that comes right back to this. So that's this guy right here. So they're one and the same. Okay. So how fast is the capability of being fast at any particular point? You got to imagine, guys, that like right here, you're at a height of y. That's y amount of rope. Y amount of rope is y amount of rope times the mass per length of rope times this. So mass per length of rope times the length, that'll give you the mass of the y length of rope. The mass of the y length of rope is equal to this times g will tell you the force of tension that you got at that moment. So if that's the case, let's talk a little bit. Yeah, okay, we've already said that. Well, let's see if we can simplify a little bit. Ft is mu yg divided by mu. That's pretty significant. Mu divided by mu is out of there. Mu divided by mu is out of there. You got yg or gy. In this case, that's true. So, well, okay. I mean, so I guess we, in a backhanded way, we just did it. This is actually the answer. What is the speed of propagation at any particular instant? Well, it's equal to this. The wave speeds up. The wave will speed up with the more tension on it. And the tension increases in a linear sense. So in a linear, why does it increase in a linear sense? Because mu is a constant and g is a constant. The only thing that makes Ft change is y. The further up you go in a linear, if you go twice the height that you were earlier, you got twice the tension in the rope, twice the speed. Now somebody might say, what are you talking about? Yeah, you got twice the tension, but you're dividing by mu. But mu is a constant. When we did it, it fell out of there. Really did come to that. So that's A. Now, the other one's a little different. The other one is asking you, what's the time? What's the time? How long does it take to get up there? That's pretty interesting stuff. Well, I'll tell you what we're going to do on that one. For that one, we got to watch out a little bit. dy is equal to dy dt, which is equal to the square root of the product gy. Y varies. The bread and butter is this right here. I got to deal with that. dy dt is equal to the square root of gy. Tell you what I'm going to do. What do you say you take dy dt equals the square root of gy, divide by the square root of gy on each side, and multiply by dt on each side? This is really, really important. You're not done. You're certainly not done. But at least you got some kind of setup here that's going to get you to where you want to go. You've got this. So I'll tell you what I'm going to do. Given that right there, what do you say you integrate each side appropriately? Integrate this guy from 0 to capital L, and integrate this guy from 0 to t, however long that's going to take. What you have here, ladies and gentlemen, integrate that. You're going to set that to the integral of the other one. You're just doing the appropriate stuff here. 0 to t, that's the whole amount of time. That's the whole amount of distance. Sounds good to me. dt is the same as 1 times dt. Not a big deal. Well, you know, you got to be careful here now. The square root of g on the bottom is a constant. It's really 1 over the square root of g, so that ain't a big deal. If you're going to integrate this, I mean, there's a lot of ways to go. I don't know what to tell you. I could take the 1 over the square root of g and take it out of there and go integral 0 to L of dy over the square root of y, which is the same as y to the negative 1, integrating that. And then you got this right here. If you integrate 1 dt, you get t. Between the limits from 0 to t, you get t. That's going to be your time. This one right here is 1 over the square root of g. That's y to the negative a half. That's y to the negative a half dy. Add 1 to the negative a half, and you get y to the half times 1 over that. So let me just see exactly what I want to do here, how you actually do this. You guys know whenever you're integrating x to the n dx, it's equal to 1 over n plus 1 x to the n plus 1. So if that's a negative a half, what's negative a half? What's negative a half and 1? It's a half. What's negative a half and 1? It's a half. The 2 right here. I'll write this a little cleaner in a second, guys. So what you do is that true? Yeah, if you take the derivative of this guy, you're going to get the half coming in front. 1 half times 2 is 1. 1 half minus 1 is negative a half. It's y to the negative a half. Y to the negative a half is this guy. And the 2 came out when the other thing. So we're good. Looks good. So when you're actually looking at it, guys, and there you're gonna integrate that. You're gonna evaluate it from here to here. So basically you got t equals, now you see a lot of stuff here. Y to the 1 half is the square root of y. Square root of y over the square root of g. You can write it like that. That's why so this is just the square root of y. That's the square root of g. Square root of y divided by the square root of g is the square root of the quotient y over g. You got the 2 right here. You're going to evaluate that from 0 to L. Well, the 0 doesn't do anything here, but the L does. The L does. You put it right here. That's how long it takes to get up there. This is meters per second per second. Meters divided by meters per second is seconds squared. The square root of second squared is seconds. Seconds times 2 is still seconds. So there you go. That's where they're talking about it on this one, guys. So there's your answer. That's 22. Let's go to 24. Is saying a traveling wave on a thin wire is given by the equation, and they gave a particular equation there. I'll write it down. Where all values are in the appropriate SI units. A and B on this one. A, what is the propagation speed of this wave? B, if the linear mass density of the string is this much, what is the tension in the string? Okay, so they gave us a little bit of data here. Let's see what we can write down and play their game. Figure out what they're doing. All right, guys, let's see where they're trying to go here with this thing. So for 24, they're telling us this. And this is y of x comma t. Y of x comma t. I'm just not writing the x comma t there. It's understood it's a function of two variables, x and t. Sine, okay guys, let me erase this. We already know we're doing traveling waves. So we got this. We got this. That's the amplitude. We'll call it Y max. You can call it A if you want. Here we go again. This thing's going to the left. This thing's going in the negative direction. There's a plus there. We know that much. We know that K is 2 pi over lambda. We know omega is 2 pi f. And there's a lot going on with that. It's 2 pi f, it's 2 pi over capital T. We've been there. We've been there, we've done that. So we know what's going on. We know what K is. We know what that is. We know how to do a lot of stuff, guys. We've been there. We know we've already delivered this speech. 2 pi f divided by 2 pi over lambda is lambda f, which is going to be the speed of propagation. Omega is 46.7. Take a look at it. That's omega. It's right there. It lines up with this guy. Omega is 46.7. K is 4.35. It's going to be a pretty big number. At the end of the day, guys, and there we are. So that's the answer for A, you guys. I think they were asking just for speed on that one. I think they were going anywhere else. B, they're saying, so they're saying, what's the speed given the circumstances that we're in? Given the circumstances that we're in. Now they're saying, what is the tension in the rope for this to be happening? So what they're saying is, okay, if the linear, kind of look at it here. If the linear mass density of the string is 3.20 times 10 to the negative 3 kilograms per cubic meter, 3.20 times 10 to the negative 3 kilograms per meter, what is the tension in the string? So they're saying, what's the tension in the string, you guys? Let's get back to the basics. V sub x, it's not V sub y this time, it's because it's going in the x direction, but it's really neither here nor there. The big thing is, it's similar to what we've talked about in the past. We're talking about this. We're talking about that right there, which is this V that we're talking about. So you can just easily erase this, and it's the same V we're talking about right there. Tell you what, let's look at it symbolically and figure out what we're doing here. Why don't you square both sides? When you're done doing that, multiply by mu. Square both sides, and when you're done doing that, multiply by mu. That's how it's going to work, guys. Simple as that. They told us that mu was 3.20 times 10 to the negative 3 kilograms per meter. We discovered the speed to be 10.7 meters per, so it's kilograms per meter. This is 10.7 meters per second squared. It's going to have the units of force, you guys, when it's all done. And let's just go. I mean, I wrote it different ways here. I got 3.688. Initially, I got 0.368812, 0.368812, or 0.369. And that's it. That is 24, you guys. How they're trying to play this. They're basically asking a simple question. What would mu have to be, the linear mass density? What would mu have to be, the linear mass density, if you're able to attain that particular speed? Forgive me. No, well, you could ask a question like that if they gave you Ft. They didn't. They're asking, forgive me, they're asking what would Ft have to be? What would the tension have to be if I give you this mu and you want to attain that speed? It's a question of solving for F sub t. Okay. If they wanted you to solve for mu, as I was erroneously about to explain, if they did ask you to solve for mu, you're going to solve for mu. You do all the mathematics to solve for mu and you're going to be fine. Okay? All right. Let's look at 49. Yeah, I was telling you guys earlier I was a little apprehensive about it, but there was no reason for my apprehension, I guess, so to speak. There's going to be refraction in the Earth's crust if there is an earthquake and is going through different material within the Earth. The speeds vary. Now, there's not going to be, I didn't mention this earlier when I had said this talked about this, you guys, but if something hits a interface, let's say there's an interface between material 1 and material 2, and there's a wave propagating. If the wave hits the interface, the boundary between material 1 and material 2, if it hits it straight on perpendicular, it hits it perpendicular to the interface. If it hits it straight on perpendicular to the interface of those two materials, there's going to be no bending. When it hit it straight, it's going to go straight. It's going to continue straight. If it hits it at an angle, that's where the speed issues, the difference in speed between the two mediums come into play. When there's a speed issue there, it'll come into play. Otherwise, if you hit something straight out, just straight on, perpendicular to the boundary between the two, there's no bending. It was going straight, it continues straight. If you hit it at an angle, the angle will change because the speeds are different. Okay? Same thing would happen if the speeds are different in the two mediums. That's what's going on here in problem number 49. So basically they're saying this, and I'll draw this a little bit and we'll kind of figure it out. 49, the Earth's mantle is denser near the core than it is near the crust. So the speed of seismic waves varies throughout the interior. Therefore, seismic waves are refracted as they travel deep within the Earth. This refraction is used to help model the density of interior layers. It allows geologists to get an idea of what is this made out of? How dense is it? The way the waves travel. A seismic longitudinal P wave traveling at 8.5 kilometers per second, they can travel that fast, encounters a region in which the propagation speed is 12.5 kilometers per second. This is crazy. This is crazy fast. These things are going as fast as rockets travel, or faster. Certainly on the order of what rockets travel, you guys. If the P wave strikes the boundary between the regions at an angle of 65 degrees with respect to the boundary, what is the angle of refraction theta in the dense region? So a seismic longitudinal P wave traveling this fast encounters a region in which the propagation speed is 12.5 kilometers per second. The faster traveling wave finds itself in a denser medium. Makes sense. Sound travels faster in water, which is much more dense than air. Sound travels faster in water than it does in air. Okay, let me draw this thing. Let me kind of go the way they got it set up is I'll do it similar to how I got it drawn, maybe a little more closely. That's all they're saying here. So it's going to go from region 1. It's going to go from region 1 to region 2, and we think something's going to happen, and we'd like to know what that is. Okay. All right, well, you remember, guys, we did talk about, I talked about refraction a little bit, right? We did talk about a number of things, actually. Here's one of them. We talked about refraction. We said, okay, let me see what I can say here, guys, actually. Trying to think exactly how I want to draw this. It doesn't have to be some kind of work of art, but let me just see here. There is let's say there's this. Here's the boundary. Here's region 1. Here's region 2. One looks kind of like that. Region 2 looks kind of like that. There is that. In this particular instance, they're trying to tell us, well, we're trying to say a lot of stuff. They're saying it hits with the boundary at a 65-degree angle. So here it is. That's a 65-degree angle here. Okay, well, be careful. Then they're claiming something like that happens. And that's an angle theta. This is the angle I want, guys. This theta is theta sub 2. This theta right here is theta sub 1. The angles are always, forgive me here. All right, guys, strike that, please. Here it is, same thing, same reality here. This right here is your theta, and that's theta sub 2. Sorry about that. Okay, there's your theta sub 2. There's your theta sub 1. The measurements that really matter, regarding this are based on what I proved to you earlier. When we said that we said sine theta 2 over sine theta 1 yeah, when we said that, the theta 2 and theta 1 have to be measured with respect to the vertical. The vertical line that crosses straight through the boundary at a 90-degree angle. This is what I was saying to you. If anything hits at a 90-degree angle going straight down like that or straight up like that, there's no refraction that takes place. It slows down. It'll slow down when it gets over to the other place or speed up. If it's the same medium, it doesn't change. True. So that's the situation here, guys. But it's got to be, whenever you're doing this, guys, you got to be dealing with it with respect to the vertical. That's it. What does that mean? That means this plus 25, this plus 25 is 90 degrees, that's 25 degree angle. This right here, I don't know what it is, but I know the math. Look over there to the far left. Is it true? Multiply by sine theta sub 1. Looks good to me. Let's go. By sine theta sub 1. Now we said sine theta and sine theta sub 2 are the same thing. So sine theta is the same as sine theta sub 2. V2 is 12.5 kilometers per second. The other one's 8.5 kilometers per second. This is the sine of 25 degrees. Man, let's do the math. Sine theta, we grind that thing out, you guys. You do it on your calculator, you're going to be fine. You're going to get right here, 9.7. I don't know, this is probably thoroughly overkill here, but all right, if you really want to do that, I mean, get the inverse sine of both sides. Get the inverse sine of the whole thing, and I showed a number of looks on how to set it up. That's good enough. Get the inverse sine of sine theta is theta. The inverse sine of this mess is going to be 38.426 degrees. What's going on here? In the faster locale, this thing's going to bend outward. It's going to fly outward that way. In the fast, as the wave comes through here, bam, it hits, and it speeds up. It hits, when you draw, I don't want to mess this up, but if you draw like a line like this and have this thing come through, once it hits here, it speeds up. It's going to travel a lot further in the same amount of time as this distance. So it's going to bend that way to go. If it was going to a slower place, pace, going to lag down and going to go right toward the vertical. It's going to be a smaller angle than 25 in this case. Well, this one's a bigger angle than 25 in this particular case, 38.426. Okay, that's 49. There's a lot of these here, guys. There's a lot that I have written there, so hopefully it's going to help you guys out. Okay, number 50. kind of a similar argument. 49 and 50, they kind of put in the same boat, so to speak. They're kind of paired off. For number 50, a seismic P wave strikes a boundary between two types of material having the same bulk modulus. Having the same bulk modulus, huh? At the boundary, the density increases abruptly. So a seismic P wave strikes a boundary between two types of material having the same bulk modulus. At the boundary, the density increases abruptly from 3,400 kilograms per cubic meter to 4,100 kilograms per cubic meter, right at the boundary. If the wavefront of the P wave is planar and makes a 25-degree angle with the boundary, what is the angle theta of refraction? So I want to draw this again, you guys. It's going to be very, very similar. Look to it. Let's see what we can say here. Leave that up here. We write the 50 right here. And let's kind of just follow a very similar argument as we proceed. Now, a lot that can be said here, guys. They call it region 1, region 2. This may be a different region. This may be a different place. Could be a different place. I mean, so when they region 1, region 2, whatever, that could be a different region 1 and a different region 2 when we're talking about it. And here's that perpendicular line. All the measurements get measured from there, even if they don't initially want to talk to you about it in that manner. So they're saying V1, V2, they're saying a whole bunch of stuff. Just debating with myself how I want to write this thing. They wrote it in a particular way, so I'm going to write it in their way. Okay, so it's not a very, through no rule, it's not the fault of anybody doing this particular problem, guys. Some of this stuff just, it's never very clear. It's not anyone's fault. It's just that communication itself is a very delicate and difficult process sometimes. And I think the more explicit you are, to the point where you're almost, it's almost too explicit, it does help. I mean, sometimes to actually get through a lot of the material that we're doing here. So the way they said it is not necessarily the easiest way to look at it, but let's figure out what they are saying. We know generally, we have already said that we got sine theta 2 over sine theta 1 equals V2 over V1. Yeah, we know that. There is a formula, the speed at which a propagation will take place. I think they use it for sound, but I think we use it for everything. It's very similar to what we were talking about earlier. Remember the F sub t over mu, the square root of that quantity? The square root of the ratio tension force divided by mu. Well, this bulk modulus has attributes kind of similar to a tension, similar to a force, I guess you could say. It's the bulk modulus divided by the mass density, rho, where the bulk modulus, in terms of magnitude, is pressure divided by deformation, divided by the amount, but the proportional amount of volume change in the deformation. That's the bulk modulus. That's the bulk modulus, you guys. And we can use this and this to kind of talk about a few things. Okay. They gave us, they said they paired these. I'm going to pretend they didn't pair them. I mean, the two problems, 49 and 50, there's similarities to them. Maybe that's why they're saying it. And they want you to know what this is. And they kind of drew it like this. And this is not necessarily something cast in stone, you guys. This one's coming in with speed v1 vector. This one's coming in with velocity v1 vector. And it's leaving here with velocity v2 vector. I'm assuming the v2 vector is going to be bigger because it's a more dense environment. They tell us that rho 1 is 3,400 kilograms per cubic meter. Rho 2 per cubic meter. So what's going on here? Well, again, I'm going with what they told us. Told us rho 1 is that. They told us rho 2 is this. We know this, and this could play a significant role in what we're doing here. If they both have the same bulk modulus, remember they're trying to play some games with us, but we're ready. We're ready. If they both have the same bulk modulus, then indeed B is the same on top for both situations. However, and this is P. This is P for pressure. It's not rho. Rho is different. And a more dense rho means slower. They're turning that around on us. It is going to go slower. Makes sense. When it was going faster, it's going to go faster in medium 2 when we were in problem 49 because it hit, let's say, right here. By the time this guy gets to here, because it's faster in here, this guy will have gone further. He'd have gone like that. He'd have gone further. So it's faster, it bends away. When it's going into a faster medium, it's going to bend away from the vertical more so than it was away from the vertical initially. Initially, it was wherever it was in regard to the vertical. Afterwards, it shoots away from the vertical because this guy will take time t to travel this distance. In the same distance, it'll take time t to travel this distance, v1 times t. v2 is faster. It's faster. If it's faster in time t, it's going to travel to here. Now look where the wavefront is. It's not like it's a little bit over. I mean, it's not like here maybe. It still doesn't look, it doesn't look radically bent, but it is kind of. Here's this guy, and here's this guy. He got bent that way. It's going that way. This guy, because it's going, well, it sure looks like it hits right here. By the time he gets here, it's fast up here. There it's slow. Here it's on the slow side. Here it's fast side. It's a lot faster. Horrible way I'm drawing this, guys, but I think I'm just trying to make the point. Well, look at that thing. That's a lot more that way. That's a lot more bent this way to go that way than this guy is. Right here. Okay, so you can see that because it's going faster. It's going from a slow place to a fast place. Here it's going from a fast place to a slow place. By the time he covers all that distance, this guy has only covered this much. So this guy covers this distance. On the bottom, it only covers just a little bit. So it's not as radical. It's closer. So this guy right here, wherever that is, it's going to be theta 2. And that's where he's going. And that's where he's going. So, okay, I think it looks pretty good. The bulk modulus is the same. This is pressure. Pressure delta V over pressure divided by the ratio delta V over VI, where delta V and VI are volumes. Delta V and VI are discussion of volume. That's pressure. That's about it. I think that's the hardest part of doing this one, you guys. So we're looking at the way they set it up. Now they said some stuff here. They said it hits here. If we're going to call this guy theta sub 2, and we should. That's him. That's going to be the theta, which is the same as theta sub 2. This guy is going to be theta sub 1. This plus 65 will give you the 90 degrees. All right, guys. So what we're talking about is here's your theta sub 1. Here's your theta sub 2 for this guy. And that's the thing. And you're making this happen. You're making this happen. So they're asking here, question that they are asking. Let's see. Just give me the theta that we're talking about. That theta down there. That theta down there, you guys. So, okay, let me get rid of, this stuff has kind of served its purpose at this point. Okay, we're still on 50, guys. Let's just figure out where it is. Do we know enough? Do we know enough to find that angle? I say that we do. To find that angle, I think we certainly know enough. We wrote all this stuff over here. I think we're okay. So stay with it and keep going. Is it true? Well, we know a lot of stuff. We know that sine theta sub 2 over sine theta sub 1 is equal to V2 over V1. Okay, we've been down this song and dance a whole bunch of times. Even here, you know, big angle means big speed. So if it takes off at a big angle, you're going into bigger speed. If it takes off at a small angle, you're going into smaller speed. Small angle divided by big angle means small speed divided by big speed. Small theta has a small sine. Big theta has a big sine. Small divided by big is the same as small divided by big. Big divided by small is the same as big divided by small. If you're going into a very fast area where propagation is going to be very fast, the theta that is found is a radically marked off theta, a theta that has departed radically from the perpendicular, from the vertical. Okay, so we got this right here. Yes, it's absolutely true. Then we also say that sound or seismic waves, they're very, very similar. Let's look at seismic waves. I think that's how they're talking about it initially anyway, for a seismic wave. As far as sound is concerned, it'd have to be very, 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 very similar to that, if not the same. But certainly, yeah, because there's a disruption in the medium, just like there is here at a radical level called an earthquake, right? But this will be for the seismic wave. V sub s for the seismic wave is the square root of the ratio B over rho. They told us V sub s of the seismic wave is the square root of the ratio B over rho. What is going on here, guys? Careful. They told us they have the same bulk moduli, but different density. So B is the same. This guy's rho sub 2 for medium 2. The way the question's asked is not the best way to ask a question, but it's okay. I mean, there's no real best way sometimes when something's written down. Sometimes you need to speak to somebody in person. Sometimes you don't. Sometimes it's very clear otherwise, but it's not always going to be that way. It's hard to do that. If they were explaining everything in a much more strenuous detail, every problem would be about this long. So not really helping anybody at that point. So there's a little bit of a dilemma they're in, I guess you could say. What's going on here? Sine theta 2 over sine theta 1 equals, wow, there's a lot going on here. The ratio of roots is the root of the ratio. So put them all underneath one radical. B over rho sub 2 divided by B over rho sub 1. The b's cancel, and you got rho sub 1 over rho sub 2. You got it to here. And I show some talk about that when you actually do that. What the heck, I might as well show it here. The ratio of roots is the root of the ratio. A ratio divided by another ratio is the first ratio left alone, multiplied by the reciprocal of the second ratio doing the dividing. The b's cancel, and there's where you get this. There's where you get the key to the whole problem, ladies and gentlemen, is right here. The key to the whole problem is right here. If you can get that under control, you're set. Now you got to be careful. There's enough there's a lot you can do. Let me stay with the non-numeric symbolism. I think it's the best way to proceed very, very oftentimes. And then at the end, we'll just make the whole thing happen. Sine theta sub 2 by itself happens if you multiply by sine theta sub 1 on each side. Get the inverse sine of both. The inverse sine of That's it. That's the symbolism that you gotta, that's where we're going. That's it. The rest is almost the triviality, I can say, of actually grinding out the numbers. What are the numbers? The numbers are theta 1. Theta 1 is 65 degrees. Rho 1 is 3,400 kilograms per cubic meter. Rho 2 is 4,100 kilograms per cubic meter. The inverse sine of the product of the sine of 65 degrees times the root of the ratio 3,400 divided by 4,100, square rooted. The inverse sine of the sine of 65 degrees, the inverse sine of the product of the sine of 65 degrees, and the square root of the ratio 3,400 divided by 4,100. Man, that's easier done than said, to be sure, guys. Let's write it right here. To two significant figures, it's 56 degrees. I'm not a stickler on that. You got enough to do, guys. I just want to see you get this right. Know what you're doing. If you know what you're doing, it becomes pretty clear. If you don't know what you're doing, that also becomes pretty clear. When I don't know what I'm doing, it becomes really clear. And when anyone does, frequently does, it eventually shows up. So theta sub 2 is 55.62 degrees. 55.62 degrees, 56 degrees to two significant figures, if they're going to ask you to do that. Okay? All right, that was 50. Let's look at 70. All right. Okay. So looking at 70, you guys. Just trying to figure it out. Okay, there it is. For 70, they are saying the equation of a traveling wave is given as, and I'll write that down and we'll kind of figure it out, where x and y are in meters and the time t is in seconds. X and y are in meters and time t is in seconds. Find the amplitude, wavelength, and angular frequency of the wave. Hint. You may need to use the trigonometric identity cosine 2 theta equals 1 minus 2 sine squared theta. All right, we got to talk. There's a number of ways you can do this, a number of ways it all comes out. Let us figure out what we want to say on this one. So they ask you a number of things. They want the amplitude, the wavelength, and the angular frequency of the wave. They give you the wave function. It's a little bit different looking than what you're used to seeing. They throw they kind of throw a pitch at you that's pretty hard to hit. So let's take a look at it and let's see what we can. What our commentary is going to be about the whole thing. Okay, it's problem number 70, guys, so I'll just take this stuff out right now. It's the last one, so I might as well erase that. At least for this. Okay, guys, so for problem 70, chapter 17, from the Katz book, here they go. They're saying y of x and t, y of x comma t, is equal to 0.50 sine squared 2.0x minus 4.0 t. Now you're thinking, okay, I can get myself out of the woods real quick. I can do all the tricks he showed me beforehand. Yes and no. I showed you a lot of tricks beforehand. I didn't explicitly work them all out, though. You got to do more than just leave it at this and then go right here and think it's going to solve the whole matter. You can't just go right there that I just pointed to and think you can solve the whole matter. It doesn't work because there's a square there. It's not looking the way we want it to look. We are trying, you guys, we're trying to get this thing, you know, this is y of x comma t is just the same as saying y. We are trying to get y max or a, and we're trying to get it to look like this. It could be plus omega t for all I know. I don't know. I better not get too innovative with it. It might be a plus omega t. My gut tells me the minus will probably stay. Now, I don't know that for sure. I got to do all the math and figure it out. Well, we're not going to go down this road completely. But I told you that famous mathematical identity, very famous mathematical identity, is used to solve a lot of stuff. And you can also simplify something squared and get an answer. It's pretty crazy stuff in its own right. Debating with myself how far to take it with you guys. We know there's a whole bunch here we can say. I'm trying to kind of derive some. I'm trying to think of something here, just straight out cold, how to do it. You could say that the sine of theta squared would be equal to e to the I theta, which would be cosine theta plus I sine theta, minus e to the negative I theta, which would be cosine theta minus I sine theta. So the cosine theta, when you do the subtraction, are gone. I sine theta minus negative I sine theta is 2I sine theta. Divide by 2I, you got sine theta. Then if you square it, see, this is what it would have been without squared. You square it, and man, that's its own dynamic, but what the heck, we entered the dance, let's dance. On the bottom, 2I times 2I is negative 4. Take these guys, e to the I theta times e to the I theta. E to the I theta times e to the I theta is e to the I 2 theta. E to the negative I theta times e to the negative I theta, even a negative times a negative is still going to be positive. That's going to be positive negative I theta. The middle guys, when you're just doing the FOIL method, ladies and gentlemen, is going to be e to the negative I theta times e to the positive I theta is e to the 0. That's 1. It's negative 1 happening twice. Negative 1 happening twice is this. That is equal to a whole bunch of ways you can do this. This right here, negative 2 divided by negative 4 is positive 1/2. This goes into here the same as plus a negative. That goes into there. If it's over 2, if it's over a positive 2, e to the I theta plus e to the negative I theta, e to the I theta plus e to the negative I theta divided by 2 is cosine theta. This right here is 1/2. The theta here is cosine 2 theta. Sine squared theta is equal to, let me just kind of see how they wrote it. This is all correct. It's not an issue. But we have to know, yeah, that's right. Okay. Right. That'll work. Yeah, absolutely. So what we can do here is we can write this as, now you can use either the cosine or the sine function to make this happen. Let me, this stuff's a little easier done than said. Let me just do this without delivering too much of a speech here, guys. Get all this over there, add a positive 1/2 cosine 2 theta on each side, subtract sine squared theta on each side. I'll tell you what, I want you to multiply by 2 on each side before you do anything. get that guy over there, get the other guy over here. Let's see what we got. We got cosine 2 theta is 1 minus 2 sine squared theta. All right, they gave us this. I'm the blockhead who loves to derive things. Yeah, this right here is, with a 2 on the bottom, is cosine 2 theta. There's another 2 on the bottom, though, so it's cosine 2 theta divided by 2. And that's where we're getting this. The fact that it's a negative means you got to make it a minus up here. Anyway, that's the argument. You go here. So we got to somehow figure out what do you want to say here with this thing. So there's a lot to be said. I mean, there's a lot you can say. So what we said here is there's a whole lot. Just want to argue this with myself a little bit. The fact that it's cosine or sine is not an issue. General form of the wave equation can be written either way, you guys, with a sine function or with a cosine function. Since we have the cosine function already present, we'll use the cosine function. But we didn't have to. Like I said, we're doing all this stuff. There's a lot of stuff coming out here. All right, similar arguments here of how you're going to proceed with this thing. So you could write it like this, or at the end of the day, you could write it like this. Something else. Now that, I'm not saying that, there's other stuff that comes into play. You'd have to put something else in here in the argument if everything else, if you're trying to make a conversion there for the same exact wave, then it can get a little messy. So this tells us a lot. That thing over there is good. We try to argue with you what you got to do here, guys. I gave a derivation here. Now, what good's the derivation if we got now the same thing could have been done with the cosine function too. You could have done if it was a cosine squared. We know that cosine squared plus sine squared is always equal to 1. So there's a whole lot we could do here. If this was equal to sine squared, if that's equal to sine squared theta, the cosine squared theta comes out to, what's a half and a half? It's 1. What's cosine squared plus cosine squared theta? Cosine squared theta plus sine squared theta is 1. 1 half and 1 half is also 1. This would have to be a plus 1 half cosine 2 theta. And it actually works out that way. When you actually, if you actually wanted to look at it, you could say, okay, well, is he telling the truth? Well, yeah, I am. Because I'm telling you, if you got this, and if you got this over 2 like that, and that's the cosine of theta, and you square it, well, here we go again. It's going to be e to the I 2 theta plus e to the negative I 2 theta plus 1 and 1 plus 2. Square the 2, you got 4. 2 divided by 4 is a half. So the 2 divided by 4 is a half. The 4 going into here, well, just put a 2 into here, and that's the cosine. And that's the cosine of 2 theta. And then there's another 2 on the bottom. There's your 1 half. So these right here, this is true. It could very well be useful sometimes. They're known as the half angle formulas sometimes. The theta here is half as big. The theta over there is half as big as the theta over here. The theta here is half as big as the theta over there. Okay, 2 theta is twice as big as this theta. This theta is half as big as the 2 theta. So they call them that. You know, it's there for you. We just did it. From here you can derive a lot of stuff. I simply put in yellow over there to the far right what they did. If they wanted to take it a little further, they could talk about both of them. And that may be of use to us. Notice when you do add them together, the 1/2 cosine 2 theta and the negative 1/2 cosine 2 theta cancel out, and the 1/2 and the 1/2 add up to 1. Cosine squared theta plus sine squared theta is equal to 1, always. So it's amazing how the consistency. Anyway, there's some fascinating mathematics out there, you guys. Right now, not our business, but we got it. You know, we know what's going on there. So what are we going to do? Well, I'm going to leave some of this up here. I mean, we worked hard to get it. Do we need all of it? I don't think so. But for right now, let's just leave it. And is there a way out of this now? Well, yeah, there's a bunch of things that happen. So here's what you're going to do. You're going to take and deal with this guy in yellow way to your far right. The one in yellow to your far right is probably going to give me an idea what the heck I need to do to find out what the heck I'm doing. It's a rough one. Let's see exactly how you want to write it. I think you put a 2 in there. You shouldn't have put the 2 in there. Oh yeah, the 2 is in there. Okay. All right, let's go. Let's go with the far. All right. Okay, they're both here. You got them. They're both here. Let me just get rid of this one. I think it's too many cooks might spoil the broth on us here. Just leave that one up there. That one up there. And we don't worry where it's going to go. We know it's going to go okay here, guys. I just got to follow that look. So you got to, let me see if I can give it some kind of a look that's going to be okay. Okay, let's do it. Let's take y of x comma t. Y of x comma t is just y. The 0.50 ain't changing anything. They never told us to change it. The sine squared is going to be converted to. There's a lot going on to do that. So we'll go with this guy again. Let's go full circle again. The sine squared, how would you do this? How would you add a positive 2 sine, add a positive 2 sine squared theta on each side and subtract cosine 2 theta and divide by 2? Well, that's what I already wrote earlier. And so we had 1 minus cosine 2 theta divided by 2. Okay, that's the one. That's big, because that's where they started us, guys. That's where they started us. So for this one right here, let's go with that. Go with that. They gave us this. From this we can get that. From that we can get this. No big deal. All right. Sine squared, you're going to put all that stuff over to the far right. 1 minus cosine 2 theta over 2. All right, so that's this guy right here is going to get converted to one minus cosine 2 theta. 2 theta, what's that? How about 2.0x minus 4.0t? True. That's the 2 theta. sine squared theta equals 1 minus cosine 2 theta, that difference divided by 2. There it is. That's the look you want to get on this. What is going on here? Well, it's going to be y equals 0.50 go. 2 times this is 4. 2 times this is 8. Deal with it. (4x), 8x, over 2. Yeah. 2 goes into here. Well, a lot's changing here, guys. 2 goes into 0.50. 2 goes into 0.50 0.25 times. This 4x and 8t are a lot different than the 2x and 4t earlier. There's a lot different here. And the amplitude is different. That's crazy. Y is going to equal something like this. Try to think here. Yeah, we got that. General form is one or the other. The 1 ain't a big deal. Since we have the cosine function already present, we'll use that. What's going on here? There's a lot going on here, but we'll figure it out. What do you say? Cosine. Let's see here. Yeah, let me just do this. Cosine, all this monkey business. I didn't put the zeros there. Man, we got enough clutter going on with this thing. Let me stop. I'm not done, but let me stop right there for a second. Got to here. True. If you make the cosine function, we're using radians now. If you make the cosine function happen earlier by pi units, or I know if you make it happen earlier by pi units or later by pi units, if you move the graph of the function over to the left and make it happen earlier by pi radians, if you make it happen earlier by pi radians or make it happen later by pi radians, what was happening earlier is going to happen somewhere else. You write it like this, either one of these, you guys. If you shift it to the left or to the right, look, I'll put it in plain English here. This thing right here, you're making everything that was happening later, you're making it happen sooner. You're bringing it over pi. If you move the cosine function over to the left, pi radians, that cosine function becomes negative cosine function. If you move it over to the right pi units, it'll also be negative cosine. So for both those. So I can use one or the other, you guys, for this reality. That's going to be useful because there is a minus here, right? So what happens is you end up getting yx comma t is 0.25 some of this stuff is 0 y of x comma t y of x comma t is 0.25 plus 0.25 cosine. Wait a minute, I thought you were saying it was minus 0.2. I thought we were saying it was minus 0.25 cosine 4x minus at. Yeah, but if you put in the argument a plus pi, it'll be a negative cosine theta. What's minus a negative cosine theta? It's plus cosine theta. Minus a negative cosine theta is that. So minus a negative cosine theta is the plus cosine theta. And that's 4x minus 8t plus pi. Plus pi makes it a negative cosine theta. What's minus a negative? It's plus a positive. And that's this. Well, this thing don't mean a whole lot. This is a constant. This just means they picked up. This just means rather than the oscillations taking place here, they're taking place higher. It's the same exact oscillations, but it's just picked up. So that ain't going to matter. The 0.25 does matter as far as location's concerned, but it doesn't matter regarding the oscillations. Doesn't not matter regarding the oscillations. That's big. So like we said, guys, like I said, you could have, and this is not an exact drawing at all by any stretch, you could have something like this, and then you got something like this. It's the same thing, just picked up. I care about the behavior of the oscillations. The plus 0.25 just means, just means it's all, the axis has been picked up. The x-axis has been picked up 0.25 units, 0.25 meters. So we got this right here. We just saw the wave function, which is, here I talk about it, I guess. We just saw the wave function, which is elevated 0.25 units, and therefore oscillates about the line y equals 0.25, with an amplitude of y max is 0.25 meters, with k equals 4 and omega equals 8, and then we just go about the business, guys, how you go about doing this. So basically, it's just elevated right here. That ain't the big deal, but the big deal is this. There's a lot of ways to go here. I just don't want to, there's a lot I don't want to erase, do want to erase, we'll see. Let's stay with this. Here we go. It's elevated. This is what I care about. What do we got? We got y max is the amplitude. I know y max is going to be 0.25 plus 0.25, but about the particular oscillations, I think the way they wrote it, y max equals amplitude, or amplitude equals y max. Who cares? It's a horse apiece. Y max equals the amplitude is 0.25 meters. Omega, wow, omega's a big deal. That's k. This is how it looks. It's a cosine. kx minus omega t plus pi. That ain't a big deal. That ain't entering into it. Here's where it goes. That's omega right here. Omega is 8 radians per second. So I guess, they asked a bunch of questions, and we're answering some of those bunch of questions, I guess you could say. We got Y max is this. That's the amplitude, right? That's this guy. We got the angular frequency is this. So what do we got? Well, we got a lot of stuff. We got k equals 4. And we know, wait a minute, we know that k is 2 pi over lambda in general. If you multiply by lambda on each side and divide by k, you get lambda is equal to 2 pi divided by k. Lambda equals 2 pi divided by k. K is 4. Lambda equals pi over 2 units or meters or whatever. I think they were talking about meters to begin with. Yeah, true. They want to know what the frequency is. Okay. If they want to know what the frequency is, we know that. Do we know that omega is 2 pi f? It's also 2 pi over capital T. If we divide by 2 pi on each side, f is equal to omega over 2 pi. What's omega? They just told us what omega was. Omega was 8 radians per second. That's 4 over pi. I didn't say it was going to be an easy one to look at. That's 4 over pi hertz. That's F. F equals 4 over pi hertz. The lambda we got, you plug in the numbers, whatever you're going to get, you're going to get. I've seen different things here. This right here, the lambda will be about 1.57 meters. Pi over 2 meters is pi over 2 meters is 1.57 meters. This thing right here, 4 over pi hertz is 1 point something hertz. I don't know if I actually grinded that one out, but it's there for us. That's the argument. Usually when you're sitting down by yourself trying to explain this to yourself, it's a lot easier. You don't need to explain it to a third party. So you're going to have an easier, you can usually whip through the stuff a lot faster. You got to make it make sense to yourself. A lot of times it's good, however, to pretend you're explaining it to a third party because there's less chance you're going to make a mistake. Or if you do make a mistake, you can kind of catch yourself as you're explaining it to yourself or to anybody else for that matter. But a lot of times it's much easier to do this stuff than it is to say it, and doing it by yourself, let's say pencil and paper, tends to be a little bit easier. The only person to whom you have to make it make sense is yourself. It's your business how you go about it, guys, but these are basically the arguments that you have to make to get there. Do you have to be this explicit? No, you're not running across 30 feet of a room, you guys. You're doing it pencil and paper, and you got to get it right on an exam or an aptitude test or some kind of high-stakes test that you're taking, or an exam for somebody else, for me or somebody else. And just know what you're doing. Get it right, okay? That takes us through all of those problems that I wanted to do from Chapter 17. Since we got this far, let me talk about the Doppler effect for 2 particular problems that are not in this book. They're in another book, and I was given permission to have, to copy them and just do them, I guess, when I talked to the book rep on it. It's from the Kutnell and Johnson book, 10th edition. Kootenell and Johnson. It's called Physics. Kootenell and Johnson are the authors. The book's called Physics. It's the 10th edition. And it's from there that I got these. There's two of them here. What the heck? Let's go through them. I think it's worth it to go through them, guys. I think it's those of you that are in my Physics 209 class. I think I've also copied these. I think I made these available to you as well. If not, I don't think there's any problem. I think I have anyway, but in case I haven't, I will make them available to you. The 120 people, non-calc version of it, definitely have it. So everybody's going to have it in front of them. I'll have this at your disposal. So you can kind of look at some of those problems as well. All right, let's take a look at two problems that are pretty interesting and how it all plays out. It involves the Doppler effect. So let's just see what we can say about it. You find problems like this in a lot of places, guys. But let me see what I can do. The question I found here, guys, was from the Kootenell and Johnson book, Physics, 10th edition. So if you don't have it, it's a good idea to maybe get a hold of a book like this. They might even have it in a library or something, or you can be able to browse some stuff. But I should have, at least the problem itself, I'm allowed to have a couple problems I can take out of there, a few problems I can take out of there and help you guys out with it. And that's what I'm doing now. And that's the permission that I got. Kootenell and Johnson are the authors. The textbook, I think it's just called Physics, probably more than just Physics, but Physics is what I got, and it's the 10th edition. And in that 10th edition on page 453, there are two really good problems that I'd like to talk about. Problems 80 and 83. So like I said, those of you in my Physics 120 class, non-calc version, non-calc treatment, you definitely should have this. I remember posting this on Canvas. Remember posting it on Canvas, and so you definitely have it. I think the 209 people do as well. If not, I'll make sure that you get a hold of it. Okay. What's going on here? What's this about? What are they asking? Well, I want you to kind of remember, it's kind of like the big brother of the whole thing here. F observer FS. Well, okay, you already saw me, if you looked at my videos, you've already heard me explain this. I even have a proof, my own proof, more or less my own proof. I've not seen it anywhere else done, though I'm sure it's been done elsewhere. It's probably the same exact way they do it in other places. They just probably maybe word it differently, and maybe my look at it is something that just made sense to me. But their version of it wasn't making sense to me. But my own version made more sense. You're going to find that a lot, guys. You're going to find that many things make a lot more sense to you when you look at it. Again, I like to derive stuff. I like to look at stuff derived. It's there for you. Bottom line is we got to get this stuff right. We got to know what we're doing, and we got to get it right. Well, this is the bread and butter to the whole thing right here, you guys. So, got to make sure it's there when we're doing it. And here we start. I'm going to erase that pretty soon and get going for it. We got problems 80 and 83 from that Kutnell and Johnson book, guys. All right. So, great problem. Problem number 80. Problem number 80. The security alarm on a parked car goes off and produces a frequency of 960 hertz. The speed of sound is 343 meters per second. As you drive toward this parked car, pass it, and drive away, you observe frequency to change by 95 hertz. At what speed are you driving? So as you're driving toward this thing, as you drive toward this parked car means the source ain't moving. V sub s, the source, V sub s, speed of source is 0. As you drive toward this parked car and pass it, and then drive away, as you drive toward this parked car, pass it, and drive away, you observe the frequency to change by 95 hertz. At what speed are you driving? My guess is, as I'm getting close to it, my frequency is really high. I'm experiencing a big frequency as I'm crowding the waves coming at me. As I'm leaving, the frequency is much smaller. As I go right by it, right next to it for an instant, I'm hearing it at the same frequency as though I were standing still. Maybe arguably we could say that. Okay, maybe we could say that. At least for a second, for a brief instance, we could. That itself could be debated. We'd have to look at that another way. But for our purposes, the maximum value of observed frequency, that you're going to encounter is as you are driving up toward, as you're driving right at the sound source. The waves are getting crowded up against your instrumentation, which is measuring this. The waves are crowding up, bunching up on you as you're coming at them. As you leave, the waves are separated from you in a sense because you're running away from the waves. So coming at them, you got the maximum frequency. Going away, you've got the minimum frequency. The difference between the two will be 95 hertz. I think that's the way it's working. So with that in mind, let's see what we can say. Well, there's a lot of looks here, guys, the way I show, and I have, all of this I have on D2L, forgive me, I'm so used to D2L, guys. All of this I have on Canvas. That should be on Canvas under Doppler effect. There's a couple Doppler effect headings that I have there. There's an intuitive way to do this simple equation. The way I wrote it up here is the real simple intuitive equation as far as I'm concerned for writing this stuff. Let's see exactly how I want to write this and how exactly I want to argue. Okay, should actually be very straightforward. Okay, so with that in mind, let me do some erasing, give myself a good amount of room, you guys. All right, you got that right there. So let's forgive me, guys. I just want to make sure my chalk's in order here. I'm missing quite a bit of it. All right, let's take a look at it. I already kind of, as I said, I was sitting down telling you this whole story. I think that's the way we're going to go. Now look at it that way. And let me I'll tell you what I'm going to do. Toward the car is going to be this. Frequency observed, T, means frequency observed toward the car. And that's going to be the frequency of the source, which doesn't change. The car's standing still. They didn't change the source on us. You are the observer. This is the speed of sound. You are the observer, O. I don't know how fast you're going, but you are going at the car. V minus or V plus Vs is irrelevant. Vs is 0. Vs is 0 on this one. So, there's a lot you can say here. There's a lot being said. Let me go away from the notes a little bit. That's toward. Away is this. You're running away from it. The car still ain't moving. So Vs is 0, the V just stays as is. This is toward, this is away. Okay, I'm kind of doing my own thing. It's very close to what I wrote in the notes, guys. I just want to kind of, you guys mind if I say delta F is equal to the big one, which I said is the toward, minus the small one, which I said is the away. It's a huge point, man. That's a very important point regarding this. Okay, so we know that. Can we do something about it? Yeah. You got the FS. Look, let's make a long story short here, guys. FOT minus FOA. FOT minus FOA is all this minus all that. Well, wait a minute. There's a V on the bottom and there's a V on the bottom. There's an FS right here and there's an FS right here. There's FS over V common to both. And the rest is just this. V plus VO minus V minus VO. There was a V on the bottom of both, so I took the V out of there. The V on the bottom of both I took out of there. The V that was on the bottom of both I took out of there. The FS that was common to both I took out of there. We got this. What is minus V? Minus a minus is plus V. Let's try it again. Minus V is minus V. Minus V minus a minus is plus V0. Plus V0 plus V0 is 2V0. V minus V is 0. That's delta F. Let me write that a little better, guys. Delta F, let's take the 2 out of there. 2Fs over V times V0. I don't know, it's a horse apiece how you want to go here. Let me show you the way I wrote it. Yeah, this is it. This is actually the toughest part of the whole problem, guys. If you're gonna, and you can show this a whole bunch of ways to get this done. Let me just let me try to make this easier to look at. That's true. That's all true. That's the same as, I don't know. It's almost it's much ado about nothing, I guess. Put the V0 right here. It doesn't matter which one you're putting where, guys. Just make sure they're there. Here's your FS. Maybe that's the easiest way to look. That's it. Guys, that's the hardest part of the whole problem. You get to here, you're set. You get to there, you're set. And like I said, I wrote it out a little more explicitly in my notes. When you look at my notes, you're going to see the same exact thing here, just a little more of the words, a little more of the numbers, explicit numbers written. But that's neither here nor there. That's not a big deal. The big deal is this. By the way, I should have written it. Okay, let's solve for u. How fast are you moving? Solve for v0. How are you going to do that? What do you say you multiply by v on each side and divide by 2fs on each side? Multiply by v on each side. Multiply by v on each side and divide by, God, all right, here it is. Let's make sure I got that right, guys. Here it is, yeah. You multiply by v on each side and divide by 2fs on each side. That's it. That's it. How fast is v? Is the speed of sound. All right, they gave me that. Delta f, they told me is 95. 2 is 2. Fs, absolutely. It's going to come out to here. You want to round it? Okay. I mean, you be careful. I don't like rounding, especially if they're making this stuff a 2% error. This is nowhere near a 2% error, guys. I mean, this thing's, 0.30 out of, 17 is, 3 over 100 over 17. That's 3 over 1700. That's 1 out of 600. That's like, that's 1/6 of 1% off. This is 1/6 of 1% off of that. So that nobody's going to, 1/6 of 1% is nowhere near the 2% error. So just know what you're doing, guys. Get the right answers when you do this. This is when it's rounded. This is the other way. Okay, that was 80. There's some other ones out there as well, you guys. I think I have it on Canvas when you look at it. I think I have the stuff written out. It should be pretty straightforward. If not, maybe I'll bring it up within the context of a lecture. But you got more than enough stuff in front of you guys that it should come out okay. All right, we're looking at this. For problem number 83, from the Kutnell and Johnson book, 10th edition, on page 553, it says this, problem number 83. Two trucks travel at the same speed. They are far apart on adjacent lanes and approach each other essentially head on, but they're far apart. One driver hears the horn of the other truck at a frequency that is 1.14 times the frequency he hears when the trucks are stationary. The speed of sound is 343 meters per second. At what speed is each truck moving? Okay, so let's talk about that a little bit. Okay, guys. Problem 83 from the Kootenil and Johnson book, 10th edition, page 543. So two trucks travel at the same speed. They are far apart on adjacent lanes and approach each other essentially head on, but far apart from each other. But they're approaching each other, and they're like, it would be head on, obviously, otherwise, but they're separated, obviously, for safety reasons, and here's how the experiment proceeds. So they're essentially viewed as head on, with there being with nobody's safety being endangered, obviously. One driver hears the horn of the other truck at a frequency that is 1.14 times the frequency he hears when the trucks are stationary. The speed of sound is what they already told us, 343 meters per second. And what speed is each truck moving? Now, they're both coming at each other, guys. This is very important. So what we have here, what are we talking about? Well, I mean, okay, you know, the bread and butter is right here, guys. We got this. We're doing a lot of this stuff. Okay. Well, let's talk a bit. I mean, it's going to sound kind of a bit on the trivial side when I do it, but let me just do it anyway. We know the frequency of the source when it's stationary is indeed equal to the frequency of the source when it's stationary. If these guys are coming right at each other, didn't they tell us that they're going at equal speeds? The observer and the source, the source is the guy with the horn. The observer is coming at the guy with the horn. He's coming right at the guy with the horn at the same speed that the guy with the horn is coming at him. The same speed that the guy with the horn is coming at him, the observer is coming at the guy with, you know. So relative to the ground, if one guy's going 80 miles per hour going toward the guy with the horn, that's sounding the horn, he's going 80 miles per hour. The guy that's sounding the horn is also going 80 miles per hour in the opposite direction right at that person that's coming at him. They travel at the same speed. They're far apart. Okay, the whole thing. One driver hears the horn at a frequency 1.14 times the same amount. Okay, tell you what I'm going to do. The observer hears the horn at 1.14 times what the horn sounds like when it's stationary. He hears it when it's stationary at Fs. When he's stationary, when it's stationary, the frequency of the source is equal to the frequency that I hear. FO equals Fs when we're both stationary. When we're both running at each other, driving at each other, I'm going to hear it. I'm going to hear that horn that you sound off. I'm going to hear it at 1.14 times the frequency that I would have heard it if we were both standing still. Okay, that's the argument. That's the whole argument. If that's the case, put Fs right here and see what happens. And these guys are equal to each other. Let's see what happens. FO is going to be 1.14. FO is going to be 1.14 Fs. Fs is this. V is V. I am the observer, and I'm running right at the source. The source is moving as fast as I am, and he's coming at me. Now, we said they're both equal. If they're both equal, VO and VS are equal to each other. Call them both VS or call them both VO, but they're equal to each other. Plus VO minus VO. Divide by Fs on each side. Divide by Fs on each side. The rest is math. The rest is math. 1.14 is the same as 1.4. 1.14 is the same as 1.14 divided by 1. This and this. What are we talking about? Cross multiply. Okay. Get a better piece of chalk, guys. All right. Let me add a positive 1.14 VO on each side and subtract 1V on each side. The observer and the source are both moving at the same speed. VO is going to be what VS is. VO is going to be 0.14, right? 0.14 over 2.14 V. What does that mean? It means 0.14 divided by 2.14, get an answer, and multiply it by 342 meters per second. VO is going to be VS, how fast are the trucks going, is equal to 22.44 meters per second. All right, guys, so run out of chalk here, of the color chalk I use here, but of the red chalk and different colors chalk, I'm kind of running out of it a little bit, but and there it is. That's it. There's other stuff that comes into play. There's a lot of problems out there, guys. I try to have as many solves as I can for you guys. Posting them is not always the easiest thing to do. Putting them on film is sometimes even a little more difficult, but it's something that we have to do, I think. I think it works out good for everybody in that regard. That is it. We will talk more. Thank you all for your time.